Okay, today we are going to go over 9C, but before we do that, let's go over a little bit of housekeeping for the rest of the semester. This is actually the um, last lecture, actually last section for the spring 2021 class. Uh, so today is Monday, April 12th, and the goal is going to be to review on Wednesday. This is week 13, guys. So a review on Wednesday. We'll have our test a week from today. So test 5, which will only be over A, B, and C. Chapter 9, I should say. Chapter 9, A, B, and C. So we'll have our last test over sections A, B, and C a week from today with a review on Wednesday. So I'll go over just everything that I kind of deem important for these 3 sections because it's a little – I want to say this chapter is a little over the place. Like it starts with modeling and then goes to linear. Today we're going to talk about exponential modeling. But because of that, I wanted to have a review day, and we didn't fall behind. Typically in these in classes, if it was a regular seated class, I promise we would have been like a day or 2 behind, and I would have caught us up by now with kind of getting rid of the review days. So it all worked out well for us, which is great. Okay, so now I'm good there. So let's kind of look at the rest of the semester. So this week is week 12, or I'm sorry, week 13. Again, we're going over 9C review. Week 14 next week, test 5 on Monday. And then I'm going to give you the last 3 lecture days to work on your final paper. The final paper, which is due, and the final exam, I should say. So final exam and final paper are due April 30th, so the last day of this month. So my goal, maybe I'll kind of change this in the schedule. So week 14, test 5, and then Wednesday, just work on your final paper. The last week, week 15, Monday, we'll use Wednesday for a review day. Okay, and we'll just review for the final on that Wednesday. And the test is 2 days later. The April 30th will be 2 days after the Wednesday of the 15th week. Okay. So, and then we'll be done. I mean, this class is almost done. I'm not feeling 100%. I don't know if that's coming through on the screen. My stomach feels really weird. Do you guys in here, Weston, Michaela, do you have any questions, housekeeping questions at all before I get started on 9C? You can give me a thumbs up if you don't have one, or you can put it in chat. I'll give you just a minute to think about it. Let me get the chat option. And then while they're thinking about questions, if they have any, please email me. If something does not make sense over these last really 3 weeks, let me know. The major thing is, test 5, last regular test is next week, next Monday. The final and the paper are due on April 30th. And my goal is to get the final paper and final test graded by the beginning of the next week, because I think grades are due that next week by like Wednesday, maybe, or Thursday. So I've got to get the final. Okay, I've got to get the final, your final grades, your overall grades for the class in by that. I think it's next Wednesday. Okay. If you think your question, just ask. No big deal. I'm going to start getting everything ready on mine. Are just super dry. Sandpaper hands going on. Okay, so today though, which actually is a pretty fun section, especially for like an intro to modeling. The last section 9B was over linear modeling, right? So if the change was linear, remember what that means is we have incremental change that's the exact same every time. So if you put $20 in underneath your bed, your mattress to save money, that is a perfect example of linear modeling, right? $20 each month or each week or whatever, and it increases by 20 over that exact time period. So 40, 60, 80, 90, or 40, 60, 80, 100, 120, and things like that. So today, though, we're going to talk about exponential modeling. Exponential modeling is different because instead of a linear change in exact amount, like $5 each month or whatever, it grows at a rate of 10 inches a day, something like that. This section actually goes over percentage changes. So what if we had, a savings account and it got such an interest rate, like a 2% interest rate a year? What can we kind of, or how can we model that? How can we make the equation for what's in that account? That's what we're going to talk about today. And we're going to talk about like half-lives. What if we know the half-life of some material and we find out that, there's so much in it, and therefore we can do like radioactive carbon dating, right? So that's how they do, whenever you're watching like the History Channel and they're like, this pyramid is so many hundred thousands of years old. Well, it's not 100,000, but it's so many thousands of years old. Well, they've done radioactive carbon dating on it. Okay. Or for that, maybe not. Maybe more like fossils. They do more radioactive carbon dating to get an exact amount because we know the half-life for certain uraniums. Okay. It's science. It's very basic stuff. You don't have to believe the alien guy on History Channel. Okay. It's basic science, basic math. Also, if we knew the half-time increase, you can do the same as well. I know it's kind of goofy to say it that way because we think of the half decrease. But if we know the time it takes to double, you can actually model it that way as well. It's kind of an inverse relationship. Instead of half the time, the half incremental amount, it's the doubling incremental amount. So let's look at this. Actually, let's start. I'm going to start in your book. Actually, your book starts in kind of a tangent. I'm going to start with the actual equations because I think that makes more sense for exponential modeling. They're really not hard equations. I just need you to pay attention to know what to plug in. Okay, pay attention so you know what to plug in. Let me get this document camera set up right. I know I hit it the other day in a meeting. I didn't mean to. It looked like I was frustrated. But it was not that big of a deal. Okay, so this is section 9C now. Okay, section 9C. And we're going to go to it on the pen in the book, so I'm not just getting off on different topics. Okay. So I'm going to actually start on page 540, which is the second page for this book, actually, in this section. I think it starts on page 539. And the reason I'm going to do that is I'm going to talk about the function, the exponential equation, okay? And it's written there, and I'm going to use the book's equation. It's Q equals Q naught times 1 plus R raised to the T. And we're going to go over what each one of these mean, okay? And this is an exponential model, okay? It's an exponential model. It's not a linear model, which looked a little different. Remember that linear model, you could model as y equals mx plus b, where you have like a rate of change. This is different. This is exponential growth or exponential decay is going to look like this. So let's go into what each one of these mean. Q, and I am just kind of stealing this from the book at the moment. So Q is the value of the exponentially growing or decaying quantity at time t. So I'm just going to say the quantity, let me be a little lazier, at time t. So that kind of gives away what t is. T is going to be time. Q naught is the initial quantity. Initial quantity. So we're going to start with an amount, and that's going to go there. Okay, so an initial quantity, and then your book says, it's when time equals 0, which makes sense. When time equals 0, would be your initial quantity. R is going to be your rate. It says the fractional growth rate for the quantity. But it's also a decay rate too. So I'm going to say the growth or decay rate. The issue is if it's a growth rate, it's going to be positive. It's a decay rate, it's going to be negative. Okay. Growth rate is going to be positive. Decay rate is going to be negative. But a big thing to remember in this one is that the percent has to be written as a decimal. So let's say let's just do an example of this first. A growth rate of a savings account at 2.5%, okay? For the formula, this is going to be 0.025, okay? That's going to be your growth rate. And again, it's a percent increase, right? So growth rate is 2.5%. So therefore, in the formula, though, it's got to be written as 0.025. Now, let's say we had a decay rate. Let's say deflation, right? Say deflation is 3.2%. Now, deflation means, of course, that this is the value that a good decreases in value each year, a percent that a good decreases in value, right? So, but and generally it's around 3. Typically it's under 3, but let's say it's 3.2%. Well, for our formula, since it's decaying, it's deflating, it would be negative. R would be negative, negative 0.032. Okay, so the formula, because it's a decay rate, it's going to go negative R into the formula. If it's a growth rate, it's going to be a positive R. And T, of course, equals the time, and it's the time that we kind of do this model. Okay, time of the modeling. Now, your book makes some really good points here. Okay, the keynotes underneath on page 540 in the green box, it's got the red dots. The unit of time used for T and R must be the same. So look, if our growth rate is 2.5% per year, that means T has to be in years. Okay, you can't have growth rate of 2.5% per year and then T be in months. You have to make these the same time unit. Okay, same with decay. You've got deflation in months or years at it deflates in value at 3.2% a year. You can't have the time in decades. Okay, these have to line up when it comes to the units, the time units. And then it says, remember that while an exponentially growing quantity has a constant relative growth rate, its absolute growth rate increases. For example, a population may increase at a constant 20% per year, but the absolute change in the population each year is always increasing because you have a percent on a percent increase, right? If we know that something grows at 5% a year, it's 5% year to year. So therefore, it's not 10% over 2 years. It's going to be more than that because you're going to have a percent growth on top of the percent growth. Okay, that's really what that's saying. Okay, well, let's look at an example. I'm going to make sure I just didn't. Yeah, well, let's look at an example. And I am going to steal the one out of your book here. Example 1 says, the 2010 census found a U.S. population of about 309 million with an estimated growth rate of 0.9% per year. Write an equation for the U.S. population that assumes exponential growth at this rate. Use the equation to predict the population in 2100. Okay, so let's start here. Q is going to be the population at 2100, right? That's going to be the amount we get done. I'm going to write the equation here again. Q equals Q naught times 1 plus R raised to the T. Okay, and I'm going to fill in what all these letters are from our equation. Q naught, now it tells us to start in 2010, right? Because we know the 2010, the amount in 2010. So the Q naught is the initial quantity. Well, our initial quantity in 2010 is 309 million. Now I'm going to be lazy and just write that as 309. So realize we're in millions. Okay. Now we've got the rate too. Rate is 0.9% per year, so years is important. So that's going to be 0.09, right? No, 009. 0.009, right? So if it's 0.9%, it's 0.009 is the growth rate. Remember, you have to move the decimal 2 places to the left. Write an equation for the population that assumes exponential growth. So let's do that. We've got everything we need for this. So we're going to clean it up. So for part A, it would be Q equals, because that's what we're going to find. Q equals 309 times 1 plus 0.009 raised to the, okay, now we need a T. Right. Okay, well, actually, we're just going to leave T. That would be the equation for the growth rate since 2010. Now I'm going to clean it up a little bit. We know how to add 1 plus 0.009. So I'm going to write this as Q equals 309 times, you don't have to write the times because it's a parentheses, 1.009 raised to the T power. Okay, 309 times 1.009 to the T power. All right. So part B says, well, what's it going to be in 2100, right? What's the predicted population in 2100? Now we got to think about this because we've got the equation. We need to know time. Well, remember, this was the time in 2010. So we need to know 2010 to 2100, the time would be 90 years. When we need to be, it needs to be in years because the growth rate was 0.09 or was 0.9% a year. Okay, so it's got to be in years. So that's going to wind up being 90. So we get Q equals 309 times 1.009, right? This is just from our equation we found before, raised to the 90. Now I'm going to put that in my calculator. Now you got to be careful when you put this in your calculator. You have to use that caret button. So it would actually, in your calculator I told you to buy, it's going to be written as 309 times parentheses 1.009. There's a caret button to the right of the calculator. I don't have it on me, or I'd show you. I'm sorry, I left it at home. But there's a caret button to the right on that calculator, and that caret button makes it into the exponent. So we're going to put 90 there. And when you do that, you should get, and I'm going to be lazy and just steal the book, it rounded to the millions. So 692 million. That's what the book says. Okay. 692 million. So, you know, it more than doubled, right? In 90 years, we more than doubled this, which is pretty neat. Okay. Pretty neat. But that's a really good example of creating the equation for exponential growth from the original kind of model of an exponential, and then finding an output from the equation. A nice A-B type question. Okay? Great. Okay. So let's do the next one, I think, which talks about population decay. So, you know, China's one-child policy was originally implemented with the goal of reducing China's population to 700 million by 2050. China's 2013 population was about 1.3 billion. Suppose China's population declines at a rate of 0.5% per year. Write an equation for the exponential decay of the population. Okay, so let's think about this. Q naught, so it's starting at, in 2013, population was 1.3 billion. So we'll do this one in billions instead of millions. So 1.3, actually, you know what? No, let's do it in millions. So, because the goal is to get down. So it's going to be 1,300 million, right? So I'm going to write this in millions. That's our initial population in 2013. Now it says it declines at a rate of 0.5% per year. So now, again, it's declining. It's not growing. So therefore, our rate's going to be negative. 0.5%, so it's got to go 0.005. That's going to be our rate. Let's make an equation for this. So again, the way equations look is Q naught equals, or Q equals Q naught times 1 plus R raised to the T. So the equation for China here, now in 2013, it was 1,300 million times 1 plus a negative, actually, 0.005. to the T, right? So we're gonna subtract here. So we get Q equals 1,300 times now 1 minus 0.005. Oh, I just want to be careful. I want to make sure this is right. It's going to be 0.995 to the T. Okay. So here's our equation starting, as long as we start in 2013. Here's our equation for China's population decrease. Now the question asks, though, would this rate of decline be sufficient to meet the original goal? So let's look and see what happens. What is predicted? And was it 2100? No, 2050. I don't think it will be. That's a lot for only 5% decrease a year. No, 0.5% decrease a year. Okay, anyway, so what is predicted in 2050? Okay, so let's see here. So Q equals 1,300 times 0.995. Now, if we started in the year 2013, that was our initial year. So we need to do 2050 minus 2013. That's 37 years. So T equals 37 years because we started in 2013. So when you pop that in your calculator, again, if I'm going to write this in my calculator, I'm going to write it as 1,300 times 0.995 raised to the 37. And I'm going to get back 1,008. Or 1,080, I should say. 1,080. So what that means, remember, this means 1.08 billion. It did not get near. I didn't think it would. That's not a huge decrease. 0.005 decrease a year is not a lot. So to go from like 1.3 billion to 700 million, I think is what they were asking. They're almost looking for, they want, to cut their population in half. They want to Thanos the population over 37 years by only decreasing by 0.05. It's just not going to work out. That's not going to do it. If the one-child policy does decrease in that rate. What is, I'm wondering what the population is now. I'm trying to hold. It's been increasing still. So even though they implemented the one-child policy, it did slow the increase. Okay, here, let's look at this actually. I just Googled, let me share my screen. It's pretty neat. And it really kind of gives you a good real world example of, nope, hold on, that's not the right screen. Share screen, I want the screen with China on it. Okay, so here is hold on a second. Guys, give me 1 second. Hold on. Yeah. You can see me, and then I'm going to share my screen with China. There we go. Okay, so you guys should be seeing the China screen now. But if you notice, the one-child policy was implemented in this area right here. Okay, I can't remember the exact year the one-child policy was implemented. But it was somewhere here. But look, see how it's growing? I mean, at a pretty fast pace. And definitely from like early 1960s to early 70s, this would be considered exponential growth. And then it slowed down. Well, now it's really slowing down. Okay, it's really slowing down. So what happened was that one-child policy actually slowed the growth. Now, it did not decrease the population. Okay, it is not showing a decrease in population, but it definitely showed a decrease in the increase, if that makes sense, of the population. This, I mean, let's think about this. From like 1980 to about 1990, if we think of the linear modeling before, if we made a slope from 1980 to 1990, it would be much steeper than the slope from, let's say, 2000 to 2010, right? If all we chose were these 2 points, the slope would be much shallower. It would be much smaller than 80 to 90. Okay, so that one-child policy, what that did is it just really slowed the growth rate down. Okay, and then India over here, though, look at this. I mean, they're shooting up. It's kind of neat. Okay, let's go back to this. So yeah, whenever population is looked at as a study, it's definitely exponential. You know what? Just because it's interesting, and it is really, I think it's interesting. So therefore, I'm going to rant about it for 2 seconds. Like, why is it an exponential growth model? Hold on, this is still 9C. Let me flip back over to my screen. Let's talk about this China one-child policy and the theory behind it. Okay, let's look up the actual date it was implemented. Implementation. Yeah, 1980. Okay, so it was implemented in 1980. And you can see that's when it really slowed down. It was like 10 years later, right? It really started slowing down. So it was implemented in 1980. And what they said was you could only have one child, okay? And if you had more than one child, you had to pay higher taxes. So in the end, if families had more than one child, they were just wealthier families. There's a lot of issues with it, like cultural issues, because boys were kind of, in China's culture, boys were like valued more because they keep the name, and there were some other cultural things as well with the males. And I don't remember them. There's a lot of really neat documentaries and literature on this policy, on the math side and the sociology, cultural anthropology side as well. Okay, but what happens? Let's think of you going backwards. Okay, actually, yeah. Let's think of. Hold on. No, let's think of I'll do my mom's side of the family. Okay, I've got my grandpa. Let's see, grandpa, and then I've got my grandma. Okay, so let's just do male females. We got male female. This is my grandfather and my grandmother. They had four kiddos. Okay, so we've got 2 females or 3 females, I'm sorry, and a male. And then this is my aunt, let's say Aunt Sharon. And then she got married and had 2 daughters. Okay. And they have, actually, let me think about this. This daughter has 1 kiddo. This daughter has 2. Ooh, actually, no, boy. Oh gosh, I'm going to run out of room. So then this is my aunt Bonnie. They had 1 daughter, right? This is my mom right here. So they got married, and I've got a brother. Okay. Now I have 2 kiddos, 2 boys. They would not like me to be there. And then my brother's not married to any kids. And then oh my gosh, yeah, okay. So my uncle here has, I should have used a much bigger page here, but this will be neat. It'll be neat to explain it. So he has a son who's married with 2 kiddos. He has a daughter who is married. I think she has 3 boys. They're young. And then another daughter who got married and had a son. Okay. Now let's think about this though. So these 2 people wound up with like 1, 2, 3, 4. Wait, 1, 2, 3, 4. Oh gosh, hold on, because this is grandkids. So 1, 2, 3, 4, 5, 6, 7, 8 grandkids who now have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 great grandkids. I mean, it's a lot going on. But the issue with this, not with this, the issue with the 1-child policy is if you go backwards here. So if you have a male and female, they have a male. Now another male and female have a female, and then they have, let's say, a male. Okay. Well, let's say this male is like, I don't know, let's say 30. Okay. So let's say he's married too. There's another female with the same thing going on, right? Male, female, male, female, male, female, right? And they have a kiddo. Okay. Now this is kiddo that's too young to work. These 2 kiddos can work. They're working age, probably, let's say, like between 20 and 30. Okay. So they're in their 20s or 30s. This group would be in their 20s or 30s. So let's say they're in their 40s to 60s. But then this group is in their 80s to 90s. So what happens, now think about this. This is the economy aspect, the sociology math aspect of this. Working age is here and here. We've got 1, 2, 3, 4, 5, 6 members of this family, this entire family tree, right? Because they can only have 1 kid. 6 members of this entire family that are of working age. Yet there's 1, 2, 3, 4, 5, 6, 7, 8, 9 members that are of non-working age. Okay. So it creates a drain on the economy if you do this for too long. The 1-child policy isn't around anymore because of this exact reason. What happened was there was a huge bubble of this group, the first group that had only 1 children. There was this huge bubble of them that were going through the population cycles, yet they in a way they weren't producing enough offspring to kind of revitalize the economy, which is a great way to think of it, right? And I'm not talking about taxes per se. It's just buying goods, trading goods, keeping the economy, there. They were struggling with that. Now, of course, it's definitely turned around. They did have a high amount of population, but this was very interesting. This policy is very interesting. There's a lot of literature is written on it in the math world and again in the sociology world. Where over here, the same kind of scenario is happening, but this group, I'll tell you right now, this group, grandma, grandpa are the only ones not working. Actually, there's a few, I think there's 1 or 2 maybe of my aunts and uncles that have officially retired, but there's a huge group in between that are in the workforce. So the amount in the workforce is much higher than the amount not in the workforce. Okay. So if you keep the rate, of it's a rate of reproduction. It sounds like an animal thing, but when you keep the rate, steady or higher, it actually is really best for the economy. You don't wind up with these weird bubbles, which is kind of what we're having with the boomers as well. Like the boomer age group, there's just a lot of them. So we're seeing some of the effects of that as well. Okay, and I'm not going to go into pros and cons of that, but that China one child policy really, this is exponential growth, right? I mean, two people create a lot of kiddos, right? This is exponential decay. Okay, so you've got, in the end, you've got these 8 individuals that really only created one. I know it sounds goofy, but they only wind up in one with one after 3 generations. Okay, where if grandma and grandpa had like 4 or 5 kiddos, they're going to wind up with a lot. You guys have seen that. You might come from large families. My family is not too large, but if you come from large families, this tree is just humongous if you start mapping it out. Okay. And that really is great for society. I mean, it's great for growth, I guess you should say. If you think growth is a good thing, it's great for growth. If you think growth is a bad thing, you'd be a proponent for the one-child policy. And I'm not going to go into pros and cons of either of them, but it is interesting, and it is a real-world math issue. Okay, back to the other stuff. Your book goes over like alternative versions of the formula, which is on page 544. Remember, you'll get to use your book on this, so it's not a big deal. And it's the half and the doubling. So I'm going to just write this down on page 544. The 3 red dots. The first one we've talked about immensely. The second 2 we haven't. So if given the doubling time, so we need the time to double here. Okay, we've got to have the time to double. If we have that, we can write the equation this way. So we still have the initial time. But it's interesting. It's 2 raised to the time overall divided by the time to double. Okay, so it's a little bit different of an equation. Okay, if we know the doubling time, then we can get this. So what is your book? Is your book giving examples? I'll give you one. If not. Okay, let's say the doubling time, the time for a bank rate to double is, let's say, 7 years. Okay, time for a bank rate to double is 7 years. So that means that's our T, capital T here, right? I want to know, well, if I put $2,000 in the account, what amount will be in the account, or let's say what amount will I have after 5 years? We'll do that one. And then we'll say for the same scenario, what about after 10 years? Now look, you gotta be careful. If it's after 5 years, we know it hasn't doubled yet. So we shouldn't have $4,000, right? If we started with 2,000, we know it takes 7 years for it to double 4,000, right? And it's only been 5 years. We should get somewhere less than 4,000. So let's plug this into the formula. So Q naught equals, now we said our initial investment was 2,000 times 2. Now I'm going to write this as if you're writing it in your calculator. Okay. So I'm going to do parentheses 2, right? That's the base. Caret. Now you have to put a parentheses here. Okay. You have to put a parentheses after this caret, because what that does is it makes sure to do this ratio first. So the little t is the time we leave it in the account, right? Remember, that's 5 years divided by the time it takes to double, 7 years. Okay. So this is what it should look like in your calculator. And pop it in there. I'm going to see what we get. 2,000. We really know it's got to be less than 4, right? 2 raised to the 5 divided by 7. I get, if we round it to the penny, 3,281.34. 3,281.34. So now I want you to try this next one. I want you to do the 10-year one. I'm going to give you just a minute to pop it in your calculator. Really, the only thing different up here is going to be the 7. Instead of 7, it's going to be 10. Because we still started with $2,000. We know the doubling time is 7 years. I'm sorry, instead of the 5, it's going to be 10. I said that wrong. So instead of it saying in 5 years, it's going to say in 10 years. So 10 divided by 7. So try that one. Okay, so let's see here. We'd have Q equals 2,000 times 2 raised to the, instead of 5 years, it's going to be 10 years now. 7. So we get 2,000 times 2 raised to the 10 divided by 7. We got 5,383.60. Okay, and which makes sense. If it takes 7 years to double, we should see that after 10 years we should see more than 4,000, right? We should see more than 4,000. Great. So now there's also doubling decay. If we know the half-life of something, okay, if we know the half-life or the amount of time given for it to be half the amount. It's the same kind of equation. Actually, the only thing different is instead of 2, it's a 1/2. Okay, so let's do an example like that one. We'll do one. I bet they have an exponential decay example in here for that. So Q equals Q naught times 1/2 instead of 2 because we're halving it, right? Raised to the T over. Now this is going to be the capital T, but for half-life. Okay, so the time it takes to half the material or the money or whatever it is. Okay. So let's look at one of these. Yeah, there you go. Okay, so if we let's look at number example 6 in your book on 547. It talks about drug metabolism. It says consider an antibiotic that has a half-life in the bloodstream of 12 hours. So I'm going to write that down. So we know T half is 12 hours. So you take this medicine, and 12 hours later, half of the medicine is in your bloodstream, right? So if it started with like 20 milligrams, then 10 milligrams will be in your bloodstream after 12 hours. So a 10 milligram injection of the antibiotic is given at 1 p.m. How much antibiotic remains in the blood at 9 p.m.? Draw a graph. I'm not going to worry about the graph, guys. You're more than welcome to look at it at the bottom of the page, and it shows kind of just exponential decrease, how it works. I'm not worried about the graph. I want the equation. So let's just do the first part. So Q equals, now we started with 10 milligrams, right? So 10 milligrams times 1/2. Now the time here. So it was given at 1 p.m. and we want to know how much is left at 9 p.m. So therefore that's going to be 8 hours. So the little t is going to be 8 hours. Divided by, we know the half time is 12. Okay. And I'm just going to pop that in my calculator. So same thing. If I'm writing this in the calculator, it's going to be 10 times 1/2 caret 8 divided by 12. That's what it's going to look like. Okay. 10 times 1/2 raised to the 8 divided by 12. And you wind up with the quantity left in the bloodstream. And your book rounds this one to a decimal place, so 6.3 milligrams. Okay, 6.3 milligrams. Which makes sense, right? If it's a 12-hour half-life, we know it's not going to go from 10 to 5, right? It's going to be somewhere between 10 and 5, I should say, because it's only been 8 hours, right? It hasn't been the full 12 hours. Pretty cool. Okay, now this homework, I'm going to be really kind of choppy with. I'm not going to give you the whole thing. Actually, I wrote this down earlier. On page 550, on those exercises, I want you to start on 1, do 1 through 9. Now I'm going to be real specific here, 1 through 9. I'm not worried about the basic exponential and logarithmic skills that it goes over, because really from this section, I want you to be able to make the model, and I want you to be able to solve the model in the way we've done it in this lecture. So 1 through 9, 27 through 33. Now on 27 through 33, they ask you like 3 different questions. I want you to just do A and B. Don't worry about making the graph on C. And then let's look at this. Let's do 41. It's like the drug metabolism question I just gave you. Yeah, 43, same thing. This is a half-life with the uranium. So it really talks about the radioactive aspect of half-life. Yeah, that'll be good. So this will be good. I know it's a lot different than what the lecture with the schedule says, but I've just decided to go this route today. So this is the homework for section 9C, which is the last set of homework for this class, which is kind of cool. Okay, the last set of homework. So let's go back to me. Yep. So remember, again, that was the last lecture for quantitative reasoning. So Wednesday, we're going to go over a review for the test. Monday, we're going to have the test. And then Wednesday review. Actually, next Wednesday, you're going to work on your final paper. I'm going to give you time to work on your final paper. Next Wednesday and really next Monday, we'll review the for the test, the final, the Wednesday after that. I'll keep you updated through email on whether we're going to have class or not. But really, this is the last regular class before the Wednesday, before the final. Okay. So if you guys have any questions, let me know. Please email me if something does not make sense. Please email me. Yeah, I know it really has flown by. This semester has gone by fast, a lot faster than I realized. And we're kind of a week ahead because I'm giving you time to work on the final paper. Okay. So make sure to get that final paper done. And yeah, have a great summer. I mean, I'll see you again in the review. I'll do all my goodbyes in the review, the review day. But if I don't see you, then I hope you have a great summer. Make sure to get that final paper done and make those fixes that I recommended in your rough draft. Make sure to go by, if you're struggling on what to do, Miss Althea and the Tutoring Center is a great resource for helping you with the paper. Just, to proof it, help you put it in the right formats, because you guys had really good topics and the topics were very interesting. And I could tell that they cared about them. Maybe not, as much as I probably care about them, but by letting you choose what to write about, I think that helped on something that's kind of math related, that's close to you. So anyway, please just get that formatting fixed. That's been the main issue from reading the paper so far. Okay, so if you don't have any questions, I'll stick around for a little bit. I'm going to stop the recording. I'm going to stick around for a little bit. If not, email me again, and I will see you all the Wednesday before. Actually, no, I'll see you this Wednesday for the review.